This video explains the internal working of the most famous and popular operational amplifier, the ua741. This operational amplifier, designed by Dave Fullagar in 1968 at Fairchild Semiconductor, owes its success to the intuition of inserting the compensation capacitor inside the chip, instead of requiring external compensation. This simple difference has made the ua741 the standard OpAmp. The ua741 is still in production and has become ubiquitous in electronics. However, speaking about the ua741, we must give credit to Bob Weidler too, because the schematic is based on the LM101 designed by Bob Weidler for National Semiconductor, which in turn is based on the ua709 and the ua702, the first monolithic IC operational amplifier also designed by Bob Weidler for Fairchild Semiconductor. We are going to show the general working of each single part of the schematic, and then we go deeper, calculating some important characteristics of this OpAmp. The path for the ua741 has been long, and here we see the main steps. The first OpAmp was a vacuum tube OpAmp by Bell Labs. It had a single inverting input. In 1947, the operational amplifier was first formally defined and named in a paper by John Ragazzini of Columbia University. The same paper introduces the first OpAmp design to have two inputs, one inverting, the other non-inverting. In 1953, vacuum tube OpAmp became commercially available. The picture portrays a vacuum tube OpAmp of 1953, but in 1947 a major turnaround happened, the birth of the first transistor in Bell Laboratories. In 1954 we had the first silicon transistor, and in 1959 the introduction of planar process made the transistor and integrated circuit stable enough for the commercialization. By 1961, solid-state discrete OpAmps were being produced. These OpAmps were effectively small circuit boards with packages such as edge connectors. In 1963, the monolithic IC OpAmp, the ua702, designed by Bob Weidler at Fairchild Semiconductor, was released. Monolithic ICs consist of a single chip as opposed to a chip and discrete parts. Almost all modern OpAmps are monolithic ICs. However, the first IC did not meet with much success. Issues such as an uneven supply voltage, low gain, and small dynamic range held off the dominance of monolithic OpAmps until 1965, when the ua709, also designed by Bob Weidler, was released. Later, Bob Weidler went to National Semiconductor, which under his guidance released the LM101, solving a variety of issues. Finally, in 1968, Dave Fullagar at Fairchild Semiconductor released the ua741, which was extremely similar to the LM101, except that Fairchild's facility allowed them to include a 30 picofarad compensation capacitor inside the chip, instead of requiring external compensation. This simple difference has made the ua741 the most popular OpAmp of all time. Since 1968, the ua741 has been produced by many different manufacturers, so you can find many slightly different versions. The schematic and some of the following explanation are taken from the book Analog Circuit Design, Discrete and Integrated by Sergio Franco. Let's see now the schematic of the ua741, which has numerous clever solutions. First, let's recognize the typical three stages of the OpAmp, the general working, and then we go deeper into each stage. The first stage is the typical input stage of the OpAmp, consisting of a differential amplifier. It provides the differential input and some gain. The second stage consists of a Darligon type configuration Q16 and Q17, which provides additional gain. The final stage is a class AB output stage to avoid crossover, consisting of Q18 and Q19, providing voltage drop to bias Q13 and Q20 connected in a push-pull configuration. to provide current gain and drive resistive loads. Here, the compensation capacitor, which has brought so much success to this circuit, which is needed to provide frequency stability to the OpAmp. Let's see the general working of this kind of OpAmp. The differential pair converts the input voltage in a current going to the output of the first stage, which produces a voltage drop proportional to the gain of the first stage on the base of the second stage. I leave a link in the description explaining differential pair. The emitter follower Q16 lets pass this voltage drop on the base of Q17 in common emitter configuration, which amplifies this voltage drop inverting the sign. Q22 in emitter follower configuration lets pass the voltage almost unchanged, providing a positive voltage on the base of Q14 and Q20. This voltage switches off Q20 and on Q14, providing current and a positive voltage drop to the load. Now let's see the general working under a current point of view. Applying a voltage to the inputs, the differential pair Q1, Q2 and the current mirror Q5, Q6 and Q7 produce a current GMV in this node here, where GM is the transconductance of the first stage. Part of the current comes from the base of the second stage. The current coming from Q16 is this one, where RO1 is the output resistance of the first stage, and RI2 is the input resistance of the second stage. You see we lose something because the output resistance of the first stage is not infinite. Knowing the base current of Q16, we get the current flowing in the collector of Q16, multiplying by beta 16. Assuming R9 much larger than the resistance looking into the base of Q17, we can say that all Q16 current comes out from the base of Q17, so the current in Q17 is this. We are at the output of the second stage now, and if we assume that the output resistance of Q13A is much larger than the resistance seen into the base of Q22, then all the collector current of Q17 goes into the base of Q22, and this is the current flowing Q22 and Q19. This current makes the voltage in the base of Q14 raising, switching off Q20 and switching on Q14, providing current to the load, so the output voltage is this one here. So this is the gain for this kind of 3 stages OpAmp, and you see that even if you lose something because of the finite first stage output resistance, nevertheless the gain is very large because the product of betas. In the end, the OpAmp converts the input voltage in a current driving the base of the second stage, where this current is multiplied by the betas of the Q16, Q17 and Q22 and supplied to the load. Of course, in the case of ua741, all the assumptions we have done aren't true, so we also lose gain because the Darlington is not perfect and because of the emitter followers in the output stages, but we'll see later the gain is still high. Now we start the analysis from the biasing circuit. This is the branch where the current is produced. Q12 and Q11 are in transdiode configuration, so the current here is equal to 733 microamps, assuming VCC plus 15 volts and VEE negative 15 volts. As you can see, the current depends on the supply voltages. For this reason, in the datasheet is specified the allowed range of the supply voltages. The reference current is then mirrored toward the first stage by this Widlar current mirror consisting of Q11, Q10 and R4. The current flowing in Q10 is calculated solving this equation, and it is equal to 19 microamps. At the beginning, when the power is just switched on, the whole 19 microamps current came from the bases of Q3 and Q4, switching them on just like Q1 and Q2, and then Q5 and Q6 and all the first stage including Q8, which provides the current to the 2 branches of the differential pair and which creates a current mirror with Q9. So the current in Q8 is copied in Q9 except for the mirror error 2 over betas. The sum of these two currents has to be equal to 90 microamps, and the fractional error of the mirror is compensated by 2 IB current coming from the bases of Q3 and Q4. This configuration creates a negative feedback which stabilizes the current in the two branches of the differential pair at 9.5 microamps, 19 off. Let's see the negative feedback. If for some reason the current in the two branches increases, then the current in Q8 increases, and so also in Q9. But because the current in the wider mirror remains constant, the excess of current goes to decrease the base current coming from Q3 and Q4, then decreasing the current in the two branches. Now let's see the function of Q7. This transistor creates, with Q5 and Q6, an improved current mirror. Q7 ensures equal collector voltage for Q5 and Q6, thus balancing the two branches of the current mirror loads. The collector of Q6 is 2 VBE above VE, plus the little drop on R8. Through Q7, the collector of Q5 is also at 2 VBE above VE, plus the little drop on R2. The current in Q7 is obtained adding the base currents of Q5 and Q6 plus the current in R3, and it is equal to 10.5 microamps. Moreover, the current taken from the branch of the differential pair is less than that taken if we add, instead of Q7, a short between the base and the collector of Q5. The biasing of the second stage is provided by the current mirror Q12 and Q13. Q13 has two collectors created with two p-type diffusions in the same n-type base region. It is like two transistors with emitters and bases linked pairwise, but this would have taken more area. Q13A, Q13B copied the Q12 current in the proportion of 75% and 25% respectively. So the current in Q13A is this, and that in Q13B is this one here. Now we calculate the second stage biasing. Since the current in Q17 is equal to that in Q13A, so 528 microamps, then we find the current in Q16, which is the sum of the Q17 base current plus the current flowing in R9, which is equal to RA times 528 microamps plus VB17 divided by R9. So the current in Q16 is 16 microamps. The current coming from the collector of Q13B is 176 microamps, and it flows entirely in Q18 and Q19, neglecting the Q14 base current. Assuming the VBE19 equals 0.7 volts, the current flowing in R10 and Q18 is 14 microamps. Subtracting 40 microamps from 176 microamps, we get 162 microamps flowing in Q19. But if the current in Q19 is 162 microamps, then VB19 is this. So considering 0.653 volts instead of 0.7 volts, we get 30 microamps flowing in R10, and considering 1 microamps as Q18 base current, we keep 14 microamps as Q18 current. With this current we get VB18 equals 0.589 volts, so the total voltage bias for the push-pull configuration Q13 and Q20 is 1.242 volts. As you see, the voltage between the bases of Q14 and Q20 is not 1.4 volts, but 1.24 volts, to keep the output BJTs not completely on and avoiding large current even without load. The push-pull BJTs are large BJTs taking 4 times the area of Q19 to be able to provide enough current to the load. So we need to limit the standby current, which would be 4 times larger than that of Q19. That's why we properly underbias Q18, limiting its VBE voltage to 0.589 volts. The base voltage of the push-pull configuration is 1.24 volts, and if this voltage were shared just with the base emitter junctions of Q14 and Q20, neglecting the resistors R6 and R7, then the standby current in the output would be this, dropping on VB14 1.24 volts divided by 2. But because we do have R6 and R7, the voltage drop on the emitter-base junctions of the push-pull configuration is less, so the standby current is around 160 microamps. As you see, this current has the same magnitude of that flowing in Q19, despite being the output BJTs 4 times larger. Now we finish the general description of the circuit talking about the transistors involved in the protection circuit, which prevents damage coming from the short of the output terminal. In this situation, Q14 transistor provides such a large current which can result in sufficient heating to cause overheating of the IC. For this reason, Q15 is added. When the current arrives around 20 mA, we have 540 mV on the base emitter junction of Q15. Switching it on, thus drawing current from the base of Q14 and limiting the output current. In the case the short is with the positive supply, Q20 draws an excessive current switching on Q21, which in turn makes current flowing in R11. The voltage drop on R11 switches on Q24 and Q23. Since Q23 is on, it steals current from the base of Q16, limiting the second stage amplification and the output current. The ua741 includes a way to compensate the input offset. As you see, this is obtained through a 10 kΩ external potentiometer. The resistance seen from these nodes is 1K parallel to 5K when the potentiometer wiper is set to the center position. So the voltage on these nodes is 8 mV above the VE. If we move the wiper from the center position, we create an imbalance in the two branches which nulls the input offsets and finally puts the output to 0 when the inputs are at 0. Before diving into the small signal analysis of each stage, let's review the AC characteristics of the common emitter with emitter degeneration, which will be very useful in the following analysis. The resistance seen in the base of the BJT is this, where R pi is this, GM is this, the thermal voltage is 26 mV, and for the ua741 we assume the beta of the NPN BJTs equals 200 and that of PNPs 50, unless otherwise specified. The resistance in the collector of the BJTs is this one, where RO is equal to the early voltage over the collector current, and in the ua741 we consider these early voltages. The resistance in looking to the emitter is this. The gain considering the output on the collector is this one here, where you see the transconductance is decreased by the loop gain 1 plus GMRE in respect to the case without emitter degeneration. If we take the output here, this becomes an emitter follower configuration and the gain is this. You can see it is more or less equal to 1 and the input voltage arrives to the output unchanged. So you see the emitter degeneration acting as negative feedback, increases the base and the output resistances and lowers the transconductance by a factor of 1 plus GMRE. I leave a link in the description about common emitter configuration. Let's see the general working of this input stage, which presents as input a differential pair consisting of an emitter follower and a common base to provide voltage gain. Let's say we apply the differential voltage in this way, thus creating an AC virtual ground on the basis of Q3 and Q4. In this case, the degenerated resistance is equal to the resistance of the emitter, 1 over Gm. So the current in the branches is GMVD divided by 4. But because of the current mirror, this current is copied in the other branch, so the total current in the output is negative Gm divided by 2 times Vd. So the transconductance of the first stage is Gm divided by 2. Since we have found the first stage transconductance, we find the gain multiplying it by the resistance C in the output of the first stage, which is the parallel of the first stage output resistance and the second stage input resistance. The first stage output resistance is the parallel of this resistance looking into the collector of Q4 and this looking into the collector of Q6. So RO1 is equal to 6.12 megaohms. The second stage input resistance is the resistance seen into the base of Q16, so it is R pi 16 plus beta 16 times the parallel of R9 and the resistance seen in the base of Q17. So the first stage gain is more or less this. Now we find the input resistance, always assuming that this point is an AC virtual ground. In this case, half resistance is this, so the total input resistance is this one here. Now let's see the common mode input voltage range, which is the range of values of the common input voltage over which the input stage will function properly, with all the BJTs operating forward active region or at most on the edge of saturation. The upper limit is reached when Q1 is driven on the edge of saturation. So the limit is VCC minus VEB8 minus the saturation voltage dropping between emitter and collector of Q1, which is 0.2 volts, plus VBE1. All this equals 14.8 volts. The lower limit is reached when Q3 is driven on the edge of saturation. So the lower limit is VE plus VBE5 plus VBE7 plus VCE3 plus VBE1 equals negative 12.7 volts. The input stage includes some interesting solutions. First, note that both the input stage and the second stage use NPN transistors. This is a clever arrangement because the easiest thing to do for biasing consideration is use a PNP input stage if we want a larger gain in the second stage, which we usually want because it allows us a smaller compensation capacitor. But using NPNs as input of the differential pair makes the input base current lower than the case with PNP because of the better beta of the NPNs. Second, this input stage is an emitter forward plus a common base configuration, so we don't have capacitances magnified by the gain, avoiding the Miller effect in input, thus improving the frequency response. The PNP input, on the contrary, would be a common emitter configuration, and it would suffer of Miller effect in the input CBC capacitances. Third, cutting by half the transconductance of the first stage doubles the slew rate and halves the value of the compensation capacitor. Let's see why. The value of the compensation capacitor is defined taking into account the baud plot of gain and frequency of the OpAmp. Here you see the two poles characterizing the OpAmp, and you see that the phase shift is near 180 degrees, which can be reached aiding the delay of the feedback line or the load capacitance, thus creating a positive feedback and instability. In order to prevent this, we had a compensation capacitor which shifts back the first pole, reducing the OpAmp phase shift at a safe value and creating a safe phase margin. Now the unity gain occurs at frequencies smaller than before, let's say 1 MHz. So we need to add a compensation capacitor between the first and second stage because we want to shift back the first pole. So this capacitor has to be large enough to become the dominant one, shifting the unity gain back at the frequency of 1 MHz. If we want to size this capacitor, we force the total gain equal to 1 at 1 MHz. And since this capacitor is the dominant one, its impedance is the only one we need to consider. So all the GM over 2V in current flows through the compensation capacitor. So the total gain is now given by GM divided by 2 times the impedance, and this has to be equal to 1. So the compensation capacitor is equal this, and it is equal in our case to 30 picofarads. But if the transconductance of the first stage had been GM and not GM over 2, the capacitance would have been 60 picofarads instead of 30 picofarads. This is important because this circuit for the first time includes an integrated compensation capacitor. Now let's see why a transconductance of GM over 2 doubles the slew rates in comparison with a transconductance of GM. The slew rate of an electronic circuit is defined as the rate of change of the voltage per unit of time. The units for slew rate are volts per microsecond. The slew rate decides the capability of an op-amp to quickly change its output. Hence, it decides the highest frequency of the operation of a given op-amp. The compensation capacitor, introduced for stability reason, limits the frequency response and limits also the slew rate, which becomes this, being the compensation capacitor the dominant capacitor in the circuit, and I01 max the maximum current coming from the first stage. Remembering that the compensation capacitor is found in this way, we can say that the slew rate is this, and you see it is the double of what it would have been if the transconductance had been GA. Fourth, the negative feedback created by the biasing circuit in red, stabilizing the current in the branches of the differential pair, it also improves the resistance seen from the virtual ground, thus decreasing the common gain, so the circuit better rejects the common signals. The second stage gain has the function to provide additional gain. In particular, Q16 in emitter-follower configuration increases the resistance seen in the output of the first stage, avoiding to excessively load the first stage. Q17 in common emitter-emitter degenerated configuration with a beta of 250 provides the additional gain. The gain of the second stage is the ratio between VO2 and Vin2. This can be seen as the product of the transconductance by the resistance seen in the output of the second stage, so the parallel of RO2 and RI3, where RI3 is the resistance seen into the base of Q22, so the input resistance of the third stage. RO2 is the parallel of the resistance in the collector of Q13A and the resistance in the collector of Q17. The transconductance of the second stage is the ratio of the output current IO2 and the input voltage Vin2, which is equal to the product of the two ratios VB17 over the input voltage Vin2 and IO2 over VB17. So the part of the input voltage dropping on R9 times the transconductance of the common emitter-emitter degenerated Q17. This is the final formula and this the result. In order to calculate the second stage gain, we also need RI3, which we'll see in the third stage analysis. Now we want to calculate the output resistance of the op-amp and the input resistance of the third stage, which is needed to calculate the second stage gain. In doing so, we consider our more usual condition, assuming to have a load of 2 kΩ and an output voltage of 5 volts. In this situation, Q20 is off and Q14 provides a current of 2.5 mA. Moreover, to simplify the schematic, we first calculate the small signal resistance of the bias circuit of the push-pull output stage. The small signal model of the configuration is this. To find RBB, we apply a voltage on the emitter of Q19 and we put to ground the other input. We can write these equations, which lead to this final result. So the small signal resistance seen in the emitter of Q19 is 174 ohms. This is the simplified schematic of the output stage considering the RBB resistance instead of the bias circuit. This is the resistance seen from the base of Q14 and this is the collector resistance of Q13B. In the end, RI3 resistance is the resistance in the base of Q22, so RPi22 plus beta 22 by the resistance seen from here, which is RBB plus the parallel of RO13B and the resistance in the base of Q14. The final value is around 9.3 megaohms. Knowing the third stage input resistance, we calculate the second stage gain and the total gain, which is the product of the first stage and second stage gains, and it is equal to 241,000. Now we calculate the output resistance considering 2 kΩ load and a current of 2.5 mA flowing in Q14. The output resistance is equal to R6 plus the resistance into the emitter of Q14, which is Rpi14 plus the resistance in from the base of Q14 divided by beta 14. Rb14 is the parallel between Ro13b and Rbb plus the resistance in the emitter of Q22, where Ro2 is the output resistance of the second stage. The output resistance is 47 ohms. The output voltage swing is the range of values of the output in which the circuit keeps working properly, so with all the BJTs in forward active region or on the edge of the saturation region. The upper value is limited by Q13b, so the upper limit is VCC minus VEC13b, which is on the edge of the saturation region, minus VBE14. The lower value is limited by Q17, so the lower limit is VEE plus VCE17 plus VEB22 plus VEB20, so the output swing is between negative 13.4 volts and 14.1 volts. Summarizing our most important results and comparing them with the datasheet, we see they are different. For example, we got 241,000 as total gain, but in the datasheet we see the typical value is 200,000. We got 2.19 megaohms as input resistance, but in the datasheet we see 2 megaohms. And we got 47 ohms as output resistance, and in the datasheet we see 75 ohms. All this shouldn't surprise us because we made some assumption about betas and early voltages, but these values depend on fabrication parameters subject to the uncertainty of the production process. Moreover, about the output resistance, we made the arbitrary assumption of an output current of 2.5 milliamps. The picture shows the ua741 die under microscope, taken from the Ken Sheriff's blog. You see the 3 stages and the large area taken by the capacitor. Here you see also the large area taken from the resistor R5, which is the 39 kΩ resistor creating the reference current spread in the circuit by the current mirrors. The resistor is large because we want it accurate, and we pay a space price for this. The other resistors in the circuit have smaller sizes even when they show a larger resistance because they are built with a different technique, but as a trade-off they are less accurate. Please leave me a comment, let me know if you liked this video, make sure you put a thumb up, click the notification bell and subscribe to my channel.